Hi, my name is Nils. I am from Aalborg University, Copenhagen, and I have the pleasure of presenting our paper, Mission Impossible Spaces, using challenge-based distractors to reduce noticeability of self-overlapping virtual architecture. Before I get to the content of the paper, I want to acknowledge the efforts of Claudio, Christian, Mantas, and Norbert. That's the four students who did all the hard work and turned this idea into reality. Virtual reality allows users to travel in ways that would never be possible in physical reality. However, when the virtual environment is larger than the available tracking space, it's challenging to support the otherwise mundane act of physically walking. Particularly, while virtual environments can be virtually infinite in size, the walker's physical movement is constrained by the bounds of the physical tracking space, and this obviously poses a problem. Redirected walking circumvents this problem by manipulating the walker's physical path to keep them inside the tracking space, thus making it possible to present a comparatively large virtual environment inside that space. The approaches to redirected walking can be broadly divided into two categories. First, perspective manipulation techniques either up or downscale the user's virtual movement. This is accomplished by applying so-called gains to the user's physical movement. Environment manipulation, on the other hand, involves reconfiguration of the virtual environment to generate self-overlapping virtual architecture. For example, you can move doors and corridors behind the user's back to change where they're walking. Regardless of the type of manipulation, a criterion for ideal redirected walking is imperceptibility. So that is, the user should not notice that they're being redirected. We can also divide approaches to reducing noticeability of redirected walking into two broad categories. Both perspective and environment manipulation can be concealed by limiting the magnitude of the manipulation. For example, you can use translation, rotation, curvature, and bending gains that are small enough to remain unnoticed. Similarly, when relying on environment manipulation, you can limit the amount of overlap between adjacent rooms to avoid detection. An alternative to sub-threshold redirection is redirection masking. So this covers a broad category of techniques that decrease noticeability by creating or awaiting opportune moments where perspective or environment manipulation can be subtly introduced. For example, gains can be applied during exposure to passive or interactive distractors, and narrative events can be used to create opportunities for redirection. While it's been shown that distractors can reduce the noticeability of perspective manipulation, it remains uncertain whether they can be used to conceal environment manipulation. For that reason, the aim of the current study was to explore how virtual distractors affect users' ability to detect self-overlapping virtual architecture. To meet this aim, we performed a within-subject study comparing two conditions, that is, virtual environments with distractors and virtual environments without distractors. A total of 23 participants recruited from the student body at the university were exposed to both conditions. For each condition, the participants were exposed to 6 interior virtual environments. All 6 included pairs of adjacent virtual rooms connected by a corridor. The environments were either physically possible or impossible. The figure you see here shows a possible space on the left where there's no overlap between rooms, and an impossible space on the right where the two rooms overlap by 50%. The 6 virtual environments used for each condition were identical except from the 6 levels of overlap between the two adjacent rooms. So we included 0% overlap, so no overlap, 15%, 30%, 45%, 60%, and 75% overlap between the two adjacent rooms. The virtual environments were displayed using an HTC Vive Pro and a pair of circumaural headphones. A single HTC Vive controller was used for interaction. We were interested in exploring the utility of distractors that can plausibly be deployed as part of a virtual reality game or narrative experience. So in our case, the participants assumed the role of a wrongly convicted prisoner, and the scenario required them to escape an empty prison. The scenario supported a simple narrative and involved repeated exposure to pairs of adjacent and potentially overlapping virtual prison cells. So the prison was comprised 12 floors, so 6 floors for each condition, and each floor included 2 potentially overlapping prison cells. The participants traveled between floors using elevators in each end of the corridor, as you can see in the figure here, where the blue area denotes the area that the user could actually walk on. To ensure that the participants entered all of the cells, they were tasked with finding, albeit not memorizing, a 4-digit code needed to open the entrance to the prison. Each digit was painted on an object, so the objects were a pillow, a box, a notepad, and a plate, distributed randomly in the cells. And only 1 digit was presented in a single cell, and the fourth and final digit was always presented in the final cell of the prison to ensure that they kept searching throughout the experience. Because we sought to explore distractors that could be embedded in a virtual reality game or narrative, we used diegetic distractors. So that is distractors that were part of the virtual environment. And these distractors were designed to both present a challenge, but also play a central role in the scenario. And specifically what we did was on half of the prison's floors where there were distractors, the participants were faced with the challenge of avoiding detection from a CCTV camera placed in one end of the corridor. And you can see that on the image here. The camera alternately rotated left and rightwards so that it wasn't facing down the corridor all the time. Thus, the participants could only avoid detection by timing their walk so that it coincided with when the camera was facing away from the corridor. We believed that this challenge would introduce additional cognitive load and thus making it less likely that the participants would attend to the distance covered when moving from one cell to the next. Initially, the participants completed a questionnaire for demographic information, so age, gender, and prior VR experience, and a consent form. Then they were introduced to the task and the scenario. Afterwards, the participants were exposed to the 12 virtual environments, so 6 overlap levels for each of the 2 conditions. And so the virtual environments were presented in 2 blocks, one corresponding to each condition. And the overlap levels and the condition orders were randomized. Because we organized the conditions into blocks, we were able to administer the NASA raw task load index RTLX after exposing the participants to each condition. And in that way, we were sort of able to get some sense of what the perceived task load was of experiencing the prison escape with and without the distractors. To quantify the noticeability of self-overlapping virtual architecture, we adopted the psychophysical approach employed by Suma et al. In their original work on impossible spaces. So that is, after exposure to each virtual environment, so each of the 12 environments, the participants performed a 2 alternative forced choice task, requiring them to judge whether their virtual environment they had just visited was possible or impossible. So this brings me to the results. First, in terms of noticeability. For each overlap level, we determined the pooled probability that participants found the overlap level impossible and fitted separate psychometric functions for the condition with and without distractors. So these 2 figures show the pooled response probabilities and standard error across participants and the fitted psychometric functions. So the detection thresholds associated with each psychometric function were defined as the overlap level at which the participants were equally likely to respond possible or impossible on the 2 alternative forced choice task. And that is so essentially when the probability of responding impossible was 0.5, so at chance level. And as apparent from the dashed line on the figures here, the detection thresholds for the condition without distractors was at 40% overlap, and for the condition with distractors, it was at 67.8% overlap. To compare the perceived task load, we calculated the total RTLX score for both conditions. So the total RTLX score is the mean of the 6 subscale ratings that are included in this questionnaire. So this chart shows the results of the subscales and the total scores for the condition without distractors blue and the condition with distractors orange. So the subscales are shown on the left and the total score is shown on the right. Our analysis focused exclusively on the total score, and the statistical analysis, that was paired sample t-tests, indicated that the condition involving distractors yielded significantly higher self-reported task load than the condition devoid of distractors. So, and moreover, after exposure to all the conditions, 20 of the 23 participants explicitly stated that they found the experience more demanding when the distractors were present. So, to conclude, the results indicate that the participants were less likely to detect overlaps when distractors were presented. That is, when no distractors were presented, they were unable to reliably detect overlaps of up to 40%. But this threshold increased to 68% when the distractors were introduced. Because the participants reported significantly higher task load after exposure to the distractors, it seems plausible that the challenge-based distractors impinged on the participants' attentional resources and made them less likely to notice the overlapping architecture. Nevertheless, we cannot be certain that the observed effect on noticeability of distractors on noticeability can be attributed solely to increased task load. For example, it's also possible that factors such as exposure time or the participant's affective state could have had an effect. And our current measures do not allow us to determine if the results were influenced by such intervening variables. Despite these caveats, we feel reasonably confident that challenge-based distractors, such as the ones used in the current study, can be deployed to mask environmental manipulation and maximize the size of virtual environments that can be explored on foot. However, future studies are needed to determine the exact cause of the observed effect, whether the magnitude of this effect is consistent across virtual and physical environments of different sizes, and whether the effect generalizes to other types of distractors. So, thank you for your attention.